If you manipulate this formula a little bit, you can get 619. Amplitude in dB will be equal to -10 log 1 plus f over fb squared. So both formula are very important, but maybe you want to base on this one because 20 log is our definition of the dB. So we're going to talk about how to get the Bode plot based on this formula. If we want to develop the Bode plot, we are going to choose several critical points. Then we connect this point, we can get a plot so that we will know what will be the frequency response. Now let's look at step by step. First, the most important point is f equal to fb. Here you can see if f equal to fb, this part will be equal to 1, and under the square root, it will be 1 plus 1, which is 2. So you will have the amplitude in dB equal to -20 log square root of 2. And that is what you should remember. The value is -3. So if f equal to fb, the amplitude of the transfer function in dB will be equal to -3 dB. This is the most important point, f equal to fb. Now let's look at other point. What if f is much less than fb? Let's say f equal to 10th of fb. Then this part will be 1 over 10. And if we calculate the square, then the number will be even smaller. Then this part can be ignored. If f is much less than fb, this part can be ignored. Then we know that the square root will only to calculate square root of 1. Then this part will be equal to 0. Then we know that the amplitude in dB will be equal to 0. That means if the frequency is much smaller, let's say 10th of the fb is equal to 0. If we continue to reduce f, let's say f is less than 10th of fb, then this part will be much smaller. Then we know that the amplitude in dB will be equal to 0. So that we know if f is less than 10th of the fb, then all the amplitude in dB will be equal to 0. Now let's look at the other side. What if f is much higher than fb? Let's say f divided by fb equal to 10. Then we know that if we square 10, it will be 100. Then this one can be ignored. Then this square root of 100 will be 10. Then if you calculate -20 log 10, you are going to get -20. That means if the frequency is 10 times of fb, then your amplitude in dB will be equal to -20. What if we continue to increase the frequency? If f equal to 100 of fb, then we know that this part is much higher. Then 1 will be ignored. Then after you calculate the square root, you are going to get 100. Then calculate the log of 100, you are going to get 2. Then the amplitude in dB will be equal to -40. That means if your f is 100 times of FB, then your amplitude in dB will be -40. Then we can see we are going to get this table. So if F equal to FB, the amplitude in dB will be equal to -3. Here you can see here, this is -3, but -3 is quite close to 0, so we can use 0 to approximate it. And if frequency equal to 2 times of the FB, then the amplitude in dB will be -6. If your frequency is 10 times of FB, then we know that the amplitude in dB will be -20. If the frequency equal to 100 FB, then the amplitude in dB will be equal to -40. And if you continue to calculate the frequency, if the frequency is 1000 of FB, then the amplitude in dB will be -60. But you don't need to, because you already see the trend. We have this point, the critical point. We know what are the amplitude in dB. Then we can draw it so that we can get the Bode plot. Now first, we know we need to identify the FB. The frequency is equal to 1 over 2 pi RC. If your circuit has been defined, then this frequency is defined. This is our break frequency, because at this frequency, we are going to see the change. So we know that if F equal to FB, it is equal to -3, right? And then if F equal to 2FB is equal to -6. So if you have this point and if you draw it, you can get a curve. So here, let's first look at the curve, right? So this is your Bode plot, the real Bode plot. But we know that if F equal to FB, the amplitude in dB will be equal to -3. It's quite close to 0. Then we can just use 0 to represent that. Then if F equal to FB, we get 0. Then if F is much less than FB, then all of them are equal to 0. Then we get a straight line. For the other side, when F is higher than FB, we are going to do the same thing. If F is higher than FB, for example, if F is 10 times of the FB, we know the magnitude in dB is -20. And if F equal to 100 FB, then the magnitude in dB is equal to -40. Then we know, in fact, we can draw a line, and this line will indicate the trend. If you continue to talk about the 1000th time of the FB, you know that it will be equal to -60. So that we can use two part or two segment of the straight line to represent the Bode plot. So that, in fact, is the approximation. We can use these two straight lines to simplify the curve so that we can get the frequency response directly and very simple. Let's summarize the step to draw the Bode plot. Here, this is the amplitude plot. We first need to identify what type of the filter this is. We only talked about the low-pass filter so that you know, in fact, this is a low-pass filter. But we are going to talk about the high-pass filter later. Anyway, if you want to draw the Bode plot, you first need to identify if it is a low-pass filter or it is a high-pass filter. Then we are going to define the break frequency. Break frequency equal to 1 over 2 pi RC. If you are given a circuit or you are given the filter, you can figure out what is the break frequency. Then put the break frequency in the middle of your frequency axis. Then if the frequency is less than the break frequency, that means the left part of the break frequency, all will be equal to 0. So here you can look at this part, this segment. If the frequency is less than the break frequency, the amplitude in dB will be equal to 0. If the frequency is higher than the break frequency, we are going to identify 2 points. One is the frequency is 10 times of the break frequency. Then the amplitude in dB will be equal to -20. So you draw a point at here. Then in fact, we know if you have this point, if you have this point, if you have the point at break frequency equal to 0, and you have the point at 10 FB, and the amplitude in dB equal to -20, in fact, 2 points can define a line. You can draw this line. But if you want to continue to figure out the frequency, which is equal to 100 of the break frequency, you can draw another point. If the frequency is 100 break frequency, then you know that the amplitude will be -40. So you can draw this line. And for this line, we know the slope of this line is -20 dB per decade. That means for each of the decade, I hope you still remember the definition of the decade. That is, the ending point is the 10 times of the starting point. So from FB to 10 FB, you have the decade. And from 10 FB to 100 FB, you have another decade. For each of the decade, the amplitude in dB will be reduced by 20 dB. So you will know the slope of this straight line. Then our amplitude plot of the Bode plot, in fact, is combined by these 2 segments of the lines. One is if the frequency is less than FB or equal to 0. The other one is if the frequency is higher than FB, then you are going to have a straight line which has a slope of -20 dB per decade. So what does this graph mean? This is the amplitude plot, indicate the frequency response of the amplitude. When your signal passes through the filter, how will the amplitude will be changed? For the left-hand side, if the frequency is lower than the break frequency, you can see the signal will pass through. For the right-hand side, if the frequency is higher than the break frequency, you can see the signal will be reduced, because this is the amplitude of the transfer function in dB. We know that if the output signal equal to the input signal, your amplitude of the transfer function will be equal to 1. And if you calculate the 20 log, get the amplitude of the transfer function in dB, you are going to get 0. So here you can see zero part means your output signal equal to the input signal. We know that for the lower frequency, most of them will pass through. If you look at this part, maybe some of the frequency close to the break frequency, they will be reduced, because we know that at the break frequency, the output signal will be equal to 0.7 of your input signal. I'm talking about the amplitude. The amplitude of the output signal equal to the 0.07 of the amplitude of the input signal. And if you calculate the 20 log, get the value in dB, you are going to get -3. That means the output signal will be reduced about 30%. If you continue to increase the frequency, if the frequency is much higher than the break frequency, you can see the amplitude will continue to be reduced. That means for the lower frequency, the signal can pass through, but for the higher frequency, the signal will be filtered out. The amplitude of the signal will be reduced. For each of the decade, they are going to be reduced by 20 dB. That's why we call this low-pass filter. It lets the lower frequency pass through, but filter out the higher frequency. Now let's look at how to draw the phase plot. Phase plot indicates the change of the phase angle. And we know that for the low-pass filter, the transfer function phase part equal to negative arctangent f over fb. We are going to do the same thing. We are going to choose several critical points. Then we can draw the phase plot of the Bode plot. First, let's figure out the most important frequency, which is the break frequency. So if f equal to break frequency, we know this part will be equal to 1. F over fb will be equal to 1. Then negative arctangent 1 will be negative 45. So you're going to get negative 45 at frequency equal to fb. Then if we reduce the frequency, if f is much lower than the break frequency, let's see f equal to 10th of the break frequency, then you can calculate this value. F divided by fb equal to 0.1. Then if we calculate negative arctangent 0.1, we are going to get a value which is close to 0. So we can just use 0 to represent that. So that we know at f equal to fb divided by 10, then the phase angle will be equal to 0. Then if we continue to reduce the frequency, you can see the phase for the transfer function will be equal to 0. So this part, we can use a straight line to represent if the frequency is less than 10th of the break frequency. They all equal to 0. Now let's look at another critical point, which is f equal to 10 times of fb. So that is our point here. So if f equal to 10 times of fb, then this part will be equal to 10. Then if you calculate negative arctangent 10, you're going to get a value which is close to negative 90. And if we continue to increase the frequency, Let's see if the frequency equal to 100 of FB. Then you know you're going to calculate the negative arctangent 100. You're going to get a value which is close to negative 90. So we can use a segment of the straight line to represent this part. If f is 10 times of FB or even higher, then the phase angle will be negative 90. And then we have these 3 points here, tens of FB, FB, and 10 times of FB. Then you can connect these 3 points. You will get the straight line, indicate the change of the phase angle. We know this straight line, the 3 segments of the straight line, in fact, is the approximation of the real body plot. So the real body plot should be like a curve, but we can just use the 3-segment straight line to represent the phase plot. It will give us the idea about how the signal will change on the phase. Okay, now let's look at an example. So here we have a filter. We are going to draw the body plot of this filter. As we said, first we need to identify what type of the filter this is. Since we get the output from the capacitor, we know this in fact is a low-pass filter. Then we are going to determine what will be the break frequency. The break frequency equal to 1 over 2 pi RC. So you're going to calculate, given the R equal to 159, which is 1000 divided by 2 pi, and the capacitance equal to 1 microfarad, we can calculate the FB equal to 1 over 2 pi RC, which is equal to 1000. Then we are going to draw the 2 plot, the magnitude plot and the phase angle plot. So first, we are going to put the 1000 frequency as the middle of our whole range. So for the amplitude plot, we know that at 1000, the amplitude in dB will be equal to 0. Then if you reduce the frequency, if the frequency is less than 1000, we can just use 0 to represent all the amplitude in dB. And if we increase the frequency, for example, if the frequency is 10 times of the break frequency, which is 10 to the power of 4, then we know that the amplitude in dB will be equal to negative 20. So you're going to, 2 points. So based on these 2 points, you can draw the straight line, the segment of this straight line to represent the slope for each of the decade is going to reduce by 20 dB. Then we will finish the magnitude plot. Now let's look at the phase plot. The same thing. We know the break frequency equal to 1000. We will put it in the middle of our frequency range. Then we know that for 1000, the phase angle is negative 45. So you get a point here. Then we identify tens of the break frequency, which is 100. At frequency equal to 100, the phase angle equal to 0. And if the frequency continue to reduce less than tenth of the break frequency, less than 100, then you will get the phase angle at 0. So you can draw a straight line here, which is equal to 0. The phase angle is equal to 0. Then we identify the other critical point, which is 10 times of the break frequency. Frequency equal to 10 to the power of 4. Then we know that the phase angle will be equal to negative 90 degrees. And if we continue to increase the frequency, then all these value of the phase angle will be negative 90. Then we have this 3 point here at 100, the phase angle equal to 0. At 1000, the phase angle equal to negative 45. And at 10 to the power of 4, the phase angle equal to negative 90. So you connect these 3 points, you are going to get another segment of the straight line. So we have these 3 segments of the straight line to represent the phase angle change of this filter. Now let's look at the other type of the filter, which is the first order high-pass filter. It is a first order because we have a capacitor here. And it is a high-pass filter because now you can see we get the output from the resistor. Previous, for the low-pass filter, we get the output from the capacitor, but now we get the output from the resistor. Then the filter changed to the high-pass filter. So if we want to get the transfer function of this high-pass filter, we are going to follow the same procedure. We are going to get the output voltage divided by the input voltage. We are going to get our transfer function. Then how to get the output? So we know that this is a series circuit. Then we can figure out the current. The current will be equal to the input voltage divided by the total impedance. Then you calculate the total impedance as R plus the impedance of the capacitor. So the current will be equal to the input voltage divided by the total impedance. Then the current multiplied by R, you are going to get the output. Then use the output divided by the input, we can get the transfer function. If you are interested, you can derive it by yourself and then compare it with the book so that you will know if your calculation is correct or not. So after we get the transfer function, we can see the transfer function equal to JF over FB divided by 1 plus JF over FB. The only difference here is for the low-pass filter, at the numerator, it is 1. For the high-pass filter, it is JF over FB. The bottom part is the same. Then we know that for FB equal to 1 over 2 pi RC, this won't change. Also, it is the break frequency. It's the same as how we calculate the break frequency for the low-pass filter. Then based on the transfer function, we can get the amplitude and the phase angle. How will the amplitude and the phase angle change? So the amplitude will be equal to F over FB divided by square root of 1 plus F over FB square. And then for the phase angle is equal to 90 minus arctangent F over FB. So here you can see that quite similar with what we learned before for the low-pass filter. For the low-pass filter and the high-pass filter, their amplitude difference is low-pass filter at the top is equal to 1, and the high-pass filter is f over fb. And for the phase angle, the low-pass filter just has this part, negative arctangent f over fb. For the high-pass filter, you have a 90 degree. So the high-pass filter, in fact, is 90 degree plus the low-pass filter's phase angle. You can see this graph indicates the magnitude and phase for the first order high-pass transfer function. You can see the difference if we compare the high-pass filter with the low-pass filter. Now, for the high-pass filter, you can see for the higher frequency, the magnitude equal to 1. For the lower frequency, you can see as the frequency decrease, then the magnitude will be decreased. And then when frequency equal to the break frequency, the magnitude equal to 0.707. And for the phase angle, it is quite similar as the low-pass filter, but it is higher of 90 degree. So if we want to draw the body plot, we know we are going to use the amplitude in dB. So we should know the according value. If f equal to fb, we know the amplitude in dB in fact is -3, but we can use 0 to represent that. And if fb divided by 2 is our frequency, then the amplitude in dB will be -6. And if the fb divided by 10 is our frequency, then the amplitude in dB will be equal to -20. The same thing, if your frequency is fb divided by 100, then the amplitude in dB will be -40, so that we know the pattern. Here you can see as the frequency decrease, then your amplitude will be decreased. So if we want to draw the body plot of the high-pass filter, in fact, you can look at this one. So if you know how to draw the body plot for the low-pass filter, the high-pass filter is quite similar, and it is quite simple. Now, as we said, first, also the most important thing is to identify what type of the filter you have. So in this case, we have the high-pass filter. Then we are going to draw the body plot for the high-pass filter. Identify your break frequency. Then for your break frequency, put it as the middle of your frequency range. So this is our break frequency. And we know that for the break frequency, the magnitude in dB is -3, but we know that we can use 0 to represent that. So here the blue curve represents the real body plot, and the straight line as the approximation of this blue curve. We use 0 to represent the amplitude in dB as a frequency, break frequency. Then we know since this is the high-pass filter, it means if you have the higher frequency, then the signal can pass through. The output signal will be equal to the input signal, so the transfer function's amplitude will be equal to 1. And if we calculate the amplitude in dB, then we are going to get 0. So if your frequency is higher than the break frequency, then the amplitude here will be equal to 0. Then if your frequency is lower than the break frequency, you can see here our frequency equal to tenth of the break frequency or equal to the break frequency divided by 100. So you reduce the frequency. If the frequency is lower, much smaller, then we know that for each of the decade, the magnitude in dB will reduce by 20 dB. So this is 1 decade from FB to FB divided by 10. The magnitude in dB will reduce by 20 dB. For another decade, from FB divided by 10 to the FB divided by 100, it will reduce by another 20 dB. So you are going to have negative 40. Then connect these 2 points, you are going to get this straight line. So this will be our magnitude plot. And for this plot, we can see for the higher frequency, the signal can pass through. For the lower frequency, the signal will be reduced. The frequency is smaller, then the amplitude in dB will be smaller. So it will filter out the lower frequency, but let the high frequency to pass through. For the phase plot, it's like the low-pass filter. Just you can think about a shift upward by 90 degrees. Because for the high-pass filter, the phase angle equal to 90 minus arctangent F over FB, so that you know if F equal to FB, then you are going to get 45 degrees. And if your frequency is tenth of the FB, then you are going to get 90. Then if you continue to reduce the frequency, we know we are going to get the 90 degree, because previously for the low-pass filter, this segment equal to 0. And for the high-pass filter, just add the 90 degree. So we know that for all the frequency, which is less than tenth of the break frequency, you are going to have 90 degree. And for the frequency which is higher, let's say 10 times of the FB, you are going to get 0. And if you continue to increase the frequency, let's say 100 of your FB, then your phase will be equal to 0. So we get another segment of the straight line. Then we have these 3 critical points. FB divided by 10, you get 90 degree. And FB, you get 45 degree. And 10 FB, you get 0. Then connect these 3 points, you are going to get a segment of straight line. So the phase plot of the body plot, in fact, is combined by these 3 segments of straight line. Now let's look at an example. Determine the break frequency for a high-pass filter. If the high-pass filter has a transfer function magnitude of negative 30 dB at f equal to 60 Hz, find the break frequency for this filter. So first we know this is a high-pass filter, and at f equal to 6 Hz, you have the magnitude of negative 30 dB. It means that this 60 Hz is less than break frequency, because this is a high-pass filter. At break frequency, you have 0 dB. Then we know that for the high-pass filter, if the frequency is less than the break frequency for each of the decade, is going to reduce by 20 dB. Then at 60 Hz, it is negative 30 dB, means it's reduced 30 dB. So we want to know how many decade is 60 Hz from the break frequency. So 30 dB divided by 20 dB per decade, we get 1.5 decade. That means 60 Hz is 1.5 decade from the break frequency, and we know that 6 Hz is at the left-hand side of the break frequency. Then we know that the 1.5 decade in fact equal to log FB divided by 60, because 60 is at the left-hand side, and it is 1.5 decade from the break frequency. So log FB over 60 equal to 1.5. So you can get FB divided by 60 equal to 31.6. Then the break frequency will be 1900 Hz.